going to start with just doing a brief recap of substitution and elimination reactions. Because as we go through, it's going to be important. It's been a little bit since we've done substitution reactions. But we're going to focus on SN2, SN1, and then E2 and E1. So for substitution, remember the 2 and the 1 is the same whether it's substitution or elimination. SN2 happens all at once. So it's a bimolecular process, bimolecular rate determining step. And so it's going to happen all at once. With SN2, we have to keep in mind stereochemistry. So SN2, because it happens all at once, your stereochemistry is going to change. You're going to invert the stereochemistry. If it started as a wedge, then you're going to add as a dash. It works best with the less steric hindrance. So since SN2 has to happen all at once, that means that the nucleophile has to come in and attack when everything is still connected. And so the less steric hindrance, the better. SN2 will not work with tertiary alpha carbons. So SN2 reactions, if it's a tertiary alpha carbon, SN2 cannot happen. There's too much steric hindrance on a tertiary alpha carbon for SN2 to happen. For SN2, we should see a strong nucleophile because it has to happen all at once, so we need something strong enough to kick that leaving group out. And then aprotic solvents favor SN2. It doesn't affect the strong nucleophile's charge. SN1, we have a carbocation that forms, so SN1 and E1 have that in common. It's a multi-step reaction, typically 2 steps. It just depends on if we have to deprotonate what gets added or not. So we form a carbocation. So since we form a carbocation, we have to make sure we pay attention to that alpha carbon. It works best with stable carbocations. So tertiary and secondary are going to be the best. It will not work with primary or methyl carbocations. We won't have a reaction. Because a carbocation forms, we're going to produce a racemic mixture of stereochemistry. So 50% wedge, 50% dash. Any strength of nucleophile can work just because the carbocation forms first. And then SN1 is favored via protic solvents. Then we look at E1 and E2. So this is a little bit more recent. So E1 and E2, right? E1, we form a carbocation. And so, therefore, we have to pay attention to the carbocation formation. Whenever you form a carbocation, so E1 or SN1, we have to pay attention to hydride and methyl shifts. Any strength of base, so now for elimination, we're focusing on the base. Any strength of base can work because the carbocation forms first. Protic solvents favor E1, and E1 reactions will always form the Zaitsev product, so the most substituted alkene. Then E2 happens all at once. Again, works best with less steric hindrance, but this one could potentially work with a tertiary alpha carbon, unlike SN2 that never could. This does need a strong base, though, since it happens all at once. You need a strong base in order to kick that leaving group out. And we can actually control the regioselectivity based on the size of the base. So a small base will form the Zaitsev product, the more substituted. The bulky or strong non-nucleophilic bases will form the Hoffman product, and we'll look at this today as well. So this is just looking at substitution versus elimination. To start, we're actually going to look at the difference between a nucleophile and a base. A lot of times they're going to be one and the same, but just because it's a strong nucleophile does not necessarily mean it's a strong base. So when we talk about nucleophiles, this is now in your slides. So this is now slide 2 within your packet. Nucleophiles are substances that have electrons to share. Nucleophiles do not necessarily need a negative charge. What you might notice, though, is most strong nucleophiles. So here we have strong nucleophiles, strong nucleophiles. Most strong nucleophiles are anions. Bless you. Right? Most strong nucleophiles are anions. Not all the time, but a lot of the time. Now up here we have strong nucleophiles and weak bases. You're going to have to pull in some of your knowledge of AP Chem to help with strength of bases. So like H2S, that's not a strong base. Halides, right? So Halides are not strong bases. If you remember, like Cl minus comes from HCl. HCl is a strong acid, so Cl minus is actually negligible in terms of basicity, right? We would say it's neutral. And so these are our strong nucleophiles and our weak bases. These more likely are going to favor SN2 reactions. Strong nucleophiles and strong bases. So you'll notice when you have a strong nucleophile and a strong base, so when they are one and the same, it can favor SN2 or E2. So strong nucleophiles and strong bases. This is what I asked in the do now. Hydroxide, most common. Strong base that's also a strong nucleophile. This OR minus, this R could be any like alkyl group. NH2 minus. So you notice that these strong nucleophiles are anions and also strong bases. And then weak nucleophiles and weak bases. So this will only be SN1 and E1. Water is a weak nucleophile and a weak base. Alcohols. Make sure you pay attention to the difference between an alcohol, CH3OH, versus NaOH. Right? NaOH is an ionic salt. That will break apart into Na plus and OH minus. Alcohols are covalent compounds. You can't break them apart. And then if you have an amine, so you have some R group. R is some carbon group connected to an NH2. There's a difference again. If this was NaNH2, that's an ionic salt. That NH2 minus can break apart. This RNH2 becomes a neutral covalent compound. And so these weak nucleophiles and weak bases can only be SN1 and E1. And then up here we have strong bases that are weak nucleophiles. So these are those strong non-nucleophilic bases. So this is tert butoxide. So when we see potassium tert butoxide, we might see, usually potassium tert butoxide is going to be the most common. This is diethylamine, right, that we might see. But strong bases and weak nucleophiles, those are your strong non-nucleophilic bases. That will only be E2. So we're looking at all of these different nucleophiles versus bases because your base has to be a proton acceptor. So it has to be likely to accept a proton, except an H. So as we go through, we have to look at all of these different considerations. So when we're looking at this, all right, we're on the next slide now. Halogens, so CO minus, Br minus, I minus. These make good nucleophiles, but they make bad bases. Because, like I said, we talked about in AP Chem, they come from strong acids. Strong acids mean a very weak conjugate base. We consider them neutral in AP Chem. Neutral compounds, water, ethanol, methanol, these are weak nucleophiles and weak bases. If we add them as nucleophiles, we looked at this in the mechanisms that we did, but if we add them as nucleophiles, we have to make sure that we use that solvent again to pull off the hydrogen to prevent any formal charges. Triethylamine is an exception. So triethylamine is this strong non-nucleophilic base. You'll see as we go through practice the common strong non-nucleophilic bases. Potassium tert butoxide, triethylamine. These are the ones that we use to favor the Hoffman product in E2 reactions. And then reactants with Na+, Li+, K-. So this would be like OH-, OCH3-. Right? These are our strong bases that come in because they're negatively charged. So they can act as a strong nucleophile or as a strong base, but that metal is just a spectator ion. So then when we look at substitution versus elimination, so when we look at this, a small, strong base is also a good nucleophile. So a small, strong base, like hydroxide. I'm going to just show both of these. Nope, there we go. All right, a small, strong base, like hydroxide. So here we have potassium hydroxide for both of these reactants. SN2 will actually compete with E2. Remember, strong base and strong nucleophile can happen all at once. So we're looking at the single-step reactions. We're looking at SN2 versus E2. We might see a mixture of mechanisms and products. So when we look at this, this is a primary alpha carbon. if we look at adding potassium hydroxide, really we're looking at adding hydroxide. So we add hydroxide with the elimination reaction. We remove the leaving group. We form this double bond. So here's the product for E2. SN2, we add the OH to that alpha carbon. The leaving group leaves. And then we get an alcohol. So we actually could have both of these forming. For this bottom reaction, we have a secondary carbon. So secondary carbon, we might see different products form. All right, so we notice here with the secondary carbon, we have 3 different potential products. Within your notes, this is already circled. But we actually have this middle alkene is the most favored E2 product. All right, it's the most substituted with the alkyl groups as far apart as possible. So the trans alkene is going to be the most favored E2 product versus SN2 that, again, the OH minus comes in, right, kicks the leaving group out, and adds to that alpha carbon. So we could potentially have E2 products and SN2 products if we have a small, strong base. So then, how do we know if one is more favored versus the other and why? So for this first reaction, E2 versus SN2, SN2 is actually slightly favored. The reason that SN2 is slightly favored, we have to think about what's happening. This is a primary alpha carbon, so it's actually a little bit easier for that nucleophile to access and substitute in for the tosylate leaving group. Now, what about the bottom one? Well, the bottom one, E2 is actually slightly favored. Both, right, we're looking at the secondary alpha carbon here. But the reason that E2 is slightly favored is that it's a little bit easier to pull off the H plus than it is to replace the leaving group. Now you look at this and you say, okay, so one's slightly favored over the other, but the biggest thing to remember is that they both will occur. So when we're looking at what are our major products, in both of these, we would expect to see products for E2 and for SN2. Now, how do we know when one is more likely to occur? How do we push one mechanism to occur over another? Well, we can also look at the solvent. We have a lot of different things that we can look at. When we look at SN2 versus E2, look at the solvent that you use. If you want to favor substitution, so if you want to push for the SN2 reaction to occur, you want to push for substitution, you use an aprotic solvent. Remember, an aprotic solvent is something like DMSO. So when we talk about aprotic, something like DMSO, THF, acetone. Those are common aprotic solvents, ones that cannot hydrogen bond. DMSO and THF are just abbreviations, not elements off the periodic table. These are just abbreviations. And then acetone also does not hydrogen bond. If you want to favor elimination, we want to use a protic solvent. Most common protic solvents that we see are water and then some sort of alcohol. I'm just going to put ROH. Methanol, ethanol. Remember, ETOH is just shorthand for ethanol. Those are common protic solvents that we see. Protic solvents can hydrogen bond. Aprotic cannot. So if we vary the solvent that we use, we can actually push one over another. So if we have a strong nucleophile, strong base, because they're one and the same, like potassium hydroxide, if we want to push substitution to occur over elimination, we just use an aprotic solvent. Use an aprotic solvent, now you're going to have SN2 as your major product. So what we could do, right, we add methanol for this first one. We add methanol. Methanol is a protic solvent. Now we're favoring the elimination product. So now instead of having both products, if we add a solvent in there, we're favoring one over another. If for the second one we use DMSO, DMSO is an aprotic solvent. Well, now we're going to favor substitution. So now we don't worry about the elimination products. We just have the product for SN2. That's going to be our major product. So what we can do is we can not only look at the nucleophile or the base that we have, but we can also look at the solvents that we have in order to push for one reaction over another. So then another way that we can push one mechanism to occur over another. So one way is the solvent, another way is temperature. So high temperatures actually favor elimination reactions. So high temperature. Now we actually will just see it say hot and cold. Right? There's no specific guideline for what's hot versus what's cold. Above or below the arrow, we're just going to see it say hot or cold or cool. So high temperatures favor elimination reactions. Now this actually ties back, I always have people say why does high temperature favor elimination? What's the reason? The reason actually ties into delta G. So if you remember, we did delta G equals delta H minus T delta S in AP Chem. That's actually that's our reason for why high temperature favors elimination. As we actually increase temperature, elimination reactions have higher entropy. And so when you increase temperature, you actually make delta G more negative, and it changes more for elimination reactions than it does substitution. And so high temperatures favor elimination reactions. This is going to be the most significant for E1 versus SN1 when you can have carbocations form, but it's still true for E2 and SN2 as well. We see this most significant for secondary and tertiary alpha carbons, but again, it's still true for everything. So high temperatures favor elimination over substitution. If we take a look at what that would look like with the mechanism down here, so we have E1 and SN1 products. So the products are already on the slide for us, but we have methanol, and then we have it at high temperatures. So methanol is a weak nucleophile, weak base. So we would expect to see a mixture of E1 and SN1 products. Carbocation would form, and then we would form our E1 and our SN1 product. But if we also vary the temperature, so now you increase the temperature, if you're at high temperatures, you'll favor the E1 product. So our major product would be the E1, the elimination product. If we look at our bottom mechanism, adding water, again, water is a weak nucleophile, weak base, so we would expect a mixture of E1 and SN1. However, if we lower the temperature, now we're favoring one mechanism over another. If we lower the temperature, well, now the substitution reaction is going to be favored. So our major product would actually be the SN1 product. So temperature and solvent are two ways that we can push one mechanism over another. And we'll see that often. So we just have to make sure that we can identify protic versus aprotic, and then just pay attention to the temperature. Now, when we're looking at decision making, I'm going to try to put all these up so then we can just talk through them. So as we go through, because what we're going to do is we're going to work through and try to figure out what reactions could potentially work, what reactions could never work. And so this is how we're going to prioritize our decision making as we go through each type of question. First, look at the degree of substitution of the alpha carbon. Is it primary? Is it secondary? Is it tertiary? If it's primary, we can rule out SN1 and E1 reactions, because SN1 and E1 reactions form a carbocation. Right? So we can't have primary carbocation. Can't have primary carbocation. It's just not stable. So if we look at our alpha carbon and it's primary, we can rule out SN1 and E1. We're not going to have a primary carbocation form. Is it tertiary? If it's tertiary, we rule out SN2. Right? Tertiary carbons are too hindered. This is why, just so if you're looking back and you're saying, why are we ruling them out? Tertiary carbons are too hindered for single-step substitution. So SN2 reactions occur all at once. Tertiary carbons are too hindered. The nucleophile can't get in and attack that alpha carbon. If it's tertiary, it's too hindered. So if it's a tertiary alpha carbon, we can rule out SN2. So just with the degree of substitution, we can eliminate different reactions. Then we look at the nucleophile. Right? We look at the nucleophile and we say, okay, is it strong? Is it neutral? Is it weak? Is it a strong non-nucleophilic base? So if it's a strong nucleophile, more than likely we could rule out SN1 and E1. Now, could you vary certain conditions to use a strong nucleophile? Potentially. But more than likely, if it's a strong nucleophile, that's also a strong base. Remember, strong nucleophile is a strong base. Right? Typically, they're one and the same. We'd rule out SN1 and E1. If it's neutral, we can rule out SN2 and E2. For a reaction to happen all at once, right? This is a concerted mechanism. We need a strong base or a strong nucleophile. If you have a strong non-nucleophilic base, that's potassium tert butoxide, triethylamine. That's E2. Right? A strong bulky base is automatically E2. Potassium tert butoxide, triethylamine, those are your common ones that you're going to see. Then we turn to solvent or temperature. So if we're left with SN2 versus E2, we look at our solvents. Protic is E2, aprotic is SN2. Right? Protic solvents favor elimination, aprotic favor substitution. If we're looking at SN1 versus E1, we can look at temperature. If it's high temperatures, it's E1. If it's cool temperatures, it's SN1. High temperatures favor elimination, lower temperatures favor substitution. Now, is it this every single time? No, we might see some exceptions. How can we vary the conditions to make something work? We might see something that doesn't follow this exact decision-making procedure. But this is just one way to help. You also have this slide. So I know there's some people who are more visual. So instead of writing it out step by step like on the last slide, you have this. Now yours is not color-coded. Yours is just black and white and gray. What I want to point out, though, is the difference with some of these that are split. So notice down the side you have the degree of substitution. If it's primary, notice it has to occur via SN2 or E2. If it's tertiary, we might see differences. But then they gave here, right, is it a strong base, weak nucleophile, strong base, strong nucleophile, weak base, strong nucleophile, and then also the percentage. So when you have a strong base, strong nucleophile, you might expect to see one over another, right, more favored. Or maybe we have a 50-50 mixture. So again, this is just a graphic to help. Does it follow this every single time? Not necessarily, because notice this doesn't tie in temperature, this doesn't tie in solvent, but it's just a way to help guide our decision making as we go through. So what I want you guys to see if you can do, on slide 10, there's something that looks like this. Now you're going to notice this is the flow chart that you have on the front page of the practice packet. But what I want you guys to do before you start filling in this flow chart is I want you to go through the questions that are on this slide. So I want you to talk to your groups and I want you to see if you can answer these questions on what's not possible. It will line up to the flow chart. So once you go through and answer the questions, try to fill in as much of this flow chart as possible. We're going to start class tomorrow with actually verifying what you filled in and also talking about the stereochemistry and the regiochemistry of each type of reaction as well.